Okay, so 13.2 Lenz's law. Now the learning goal here is define the electromagnetic induction. So you are inducing magnetic field and the induction of the current, so inducing current. Define the used Lenz law to predict the direction of the induced current. Now, we did see that electric current has ability to create magnetic field. What does it mean? You have a wire. If you have current, you have magnetic field, right? See, you have current here, so it create a magnetic field. And how do you do that? Right hand rule, just you do it, a circle around that. Again, your thumb in the direction of the current tells me that the back of the wires go up and in front it's go down. So that would be the direction of the magnetic field. So the current can create magnetic field. Could it work the other way? Could magnetic field actually producing the current? Perhaps yes. We call this process electromagnetic induction because you are inducing current, changing magnetic field to induce the current. We'll see that. Any changes in magnetic field near conductor inducing a voltage. So if I change magnetic field, I'm forcing the electron inside the wire to move. So I am forcing or just making voltage across that conductor, right? So that's why it's inducing electric current in that conductor. So here, factor that affects inductions. If you use the coil conductor instead of having just a wire and change a magnetic field to force the electron moving, if I choose to have this coiled wire or the coiled conductor, it has ability to create more induced current and create this process better. Now, number of loops. Of course, if you have more loops inside this coiled, you will get more induced current. Speed of conductor. If you if faster the object moves in the magnetic field, they create a larger chain magnet. So you will see that much more better. Just doing an example, it's going to be very abstract right now. But when I have this magnet, which is have a north and south pole and has this magnetic field around that, I just move it around. So when you move it around, you're changing the magnetic field around these wires, right? So faster you do this movement means you're changing the magnetic field around the wire. So the larger current will be produced. So the speed of conductor will actually matter. So the strength of the field, if I use a stronger magnet here to produce that change of the magnetic field here, of course, I'm producing larger current. So keep that in mind. We're doing a lot of activity and you will understand better. It's just very abstract concepts. Maybe it's a good idea when I'm done coming back to this again and tell you one more time so it can make more better sense, right? Any question? Now we now see a current can produce magnetic field. We just see it. But in which direction will the current travel? Uh, that's why we use the Lenz law. Okay. Now I'm gonna read that, but again, I'm gonna do a question for you. If a changing magnetic field induces a current in a coil, the electric current in such a direction that its own magnetic field opposes the change that produces. Wow. So kind of confusing, right? Don't worry. We do the Lenz line. We'll see that. Let's look at these questions and we will actually go back to that law, see if that really makes sense with what it said. Now, see that is we have a kind of solenoid, right? It's a coiled wire. I have a magnet. Now, The motion of this magnet is toward. It's toward. Actually, it doesn't make sense because we need to have a south, right? South is here. The motion of this magnet is toward this wire. Now tell me, if I bring this magnet closer, closer, closer to this wire, do I increase the magnetic field here or I decrease the magnetic field? Imagine this is far and I might bring it closer, 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 closer. As it's getting closer, does the strength of the magnetic field around this wire increasing or decreasing? Anyone? Again, the magnet is very far, so it's barely feel the magnetic field. But as I bring it closer, it feel more magnetic field around, right? Does that make sense? When you bring it very close, it will feel the presence of that magnet. So the magnetic field is increasing when you bring this N from far to here. But the nature doesn't like that change. The nature won't oppose that change. Okay? That's why it need to make sure that it's getting away. Getting away means you need to repel that, right? So to repel that, it creates a magnetic field that repels. So if this is N, so it produces a current in such a way that produce an N pole here at this side. Make sure that this N pole and this N pole repel it. Okay? Because when you bring it, you will have a lot of magnetic field here. It doesn't like that a lot of magnetic field is here. So you need to push it away. So it's going to be N. Of course, it's going to be S. And we learned the the laws, how to, if you know the N and south pole, how to predict the currents. What you do, your thumb in the direction of the N, your forefinger will tell you the direction of what? Current. So at the back is go up and in front goes down. That would be the direction of the current using the right hand rules. So in front go down and at the back goes up, right? That would be the direction of the current induced. Mhm. Now, this is induction. Any question? If we go back to the Lenz's law, if a changing magnetic field induced a current in a coil, the electric current is in such direction that its own magnetic field opposes the change. See, I told you, you bring it forward, you will have a lot of magnetic field around this coil. It doesn't like it. The nature need to reduce it. So it produce N pole here to kind of repel this change. Just push it away, make sure it's not increasing anymore. So N would be here and S here, and from that you will have an induced current. Okay. Now I'm going this. Now, what happened if you have a your magnet is here and you're trying to move it away? So you try to move that away. Now the magnetic field around this coil will change. You try to move it away, so you're reducing the magnetic field around the coil. When you're reducing the magnetic field, nature doesn't like it. It need to oppose that change. So it would need to track that. So it's producing the south. Make sure when it's moving away, this is reducing. So to attract this one, so make sure it's not happening. So, and that would be north. Again, using the right hand rule for solenoid to predict the direction of the current. So my thumb going to direction N. So my forefinger going up in front of the wire and going down at the back. So up in front, going down at the back. Sense?
Miss, so when you
Mm-hmm.
say like the like strength of the magnetic field is going to like decrease,
Mm-hmm.
like what do you mean by that? Like, do you mean like the magnetic field of the coiled wire, or are you talking
Yeah.
about like the magnet?
So good. I want you to be with me and answer my question. So when we have this coil, there is no current here, right? When you just have your this magnet and this is staying here, nothing happened. You just have the magnetic field due to this magnet, right? That will be around this coil. And when it's close, would it be a strong magnetic field around the coil or weak magnetic field?
Stronger,
Strong, right? When you move it away, the magnetic field around the coil would be what? Decrease or increase?
decrease.
Decrease, right? So you're changing by moving this away, you're changing magnetic field around the coil, right? Is it? By moving
Yeah,
that away,
initially
I'm
you
changing
said
that.
like you said the coil had like no like current like.
Exactly, no
What do you
current,
mean by that?
nothing. So changing the magnetic field around the current will induce the current in such a way that oppose that change. Now, to oppose that change, it need to attract this one toward, just pull this one toward itself, right? Producing S. Doesn't like that. It's going away. So producing S, and here would be no, north. And from that, you can predict using your right hand rule, predict the induced current. This is going to be induced current, right? Induced current means you do change the magnetic field, so the electron field they need to move and producing current. Okay, so right hand, this is going up in front. The induced current gonna be in this way, in front, down at the back. Any other question?
Since it's like two objects and like both of the objects have a magnetic field, so like which one is it affecting?
Oh, okay. Wait. You have two object, both magnetic field. Do you mean before we do the movement or after we do the movement?
Before?
Before we doing the movement, I'm just talking about this one, right? This picture. You just have one magnetic field, and this is due to the magnet you have here. This is the only magnetic field you have. There was nothing here, right? Before you move it. After you move it, you are inducing the current inside the coil. This is inducing the current. This
Okay.
current will not last forever. This current will be there until this feel a change, You move it, it feel that need to produce the current in this direction. If you move it closer, again, the direction of the current will reverse. You do back, forth, you're producing the alternative current. If you do it continuously, do that. But if you just do it one time and you stop, you won't have the current, right? Because the changing in magnetic field need to constantly happen if you want to keep that current going.
So why doesn't a coil initially have like a magnetic field then?
No, initially the coil doesn't have magnetic field. This magnetic field, I put it here as a nurse, is after the induction, not before. Before was nothing.
No, I mean like why?
Why what? State again.
I mean like why does it initially like not have the like magnetic field? Like that's what I mean.
We don't need it. Why we would do that? So in this setup, there is no magnetic field. See, we don't have any. This is the galvanometer, right? It's just measuring the voltage created across this 2 point. Okay, voltmeter here. So we don't need anything. We just want to do this setup. Just wind some wire around a metal. So cylinder metals to have that shape. And then we're trying to change magnetic field around that, and we try to see if there is any current produced or not, right? Don't need it because it's inducing some current, and we want to measure that. Changing magnetic field will induce the current and create the
Okay,
magnetic, make it like a magnet, right? Because I'm not in your head, you need to keep pushing and ask me question and clarify your understanding. If there is any further question, just is the Angelina, right?
yeah, it's good.
Okay. If there is any other question, please ask. I'm sure that other will benefit, right? One. So this is other questions. Here again, we will have this and south. You moving that toward, since like we have done one of the question, I'm gonna do that. So moving that toward, you're increasing this magnetic field here. So it doesn't like it. So you need to repel it. So we produce N pole here to repel that. And here is south. Now your job is to use your right hand to predict the direction of this current, induced current. So the thumb will be in the direction of N. So at the back, your finger going up, in front going down. So that would be the direction, in front going down, and the back going up, right? Now B, moving away, we did it kind of moving that away. So decreasing magnet, it doesn't like it. So it proved as pole here and north pole here. Then you need to use the right hand rule to predict the direction of current. So your thumb going through N and your forefinger going down at the back, going up in front. So that would be up here in front, going up, and then the back go down. Now, part C. Can anyone tell me if you have south and north and we'll try to pull this one away, would it create the N or S here? We're doing C. Would at this part would be create N pole will be created here or south?
Sorry, miss.
Who's that?
It's Ben. I just joined.
Okay, Ben. I'll make a note and change it later.
Yeah, and also sorry. I didn't do the test last week.
Okay, Ben. Give me a second. I need to finish this slide because I'm recording that. Give me a minute. So, can anyone tell me if you move that away, would it be north or south? So again, you're moving that away, so it doesn't like it. You need to attract it. So it would be north, right? To grab this, it's gonna be north, it's gonna be south. Again, you're using the right hand rules. Your thumb going to the direction of north. So at the back, the forefinger going up, in front going down. You have to really do that to understand what I say. And here you moving the magnet toward this coil. What happened? Should I have north or south here? If you're moving that toward. Again, the nature doesn't like it. When you're moving that something toward, you need to repel that. So it should be what? Should be south. If you want to repel it, should be south. Here is north in right hand rule. So thumb in the direction of the north, going up in front of the coil, going down at the back. And that's it. I'm gonna quickly go through the alternative currents. So here we did see the Lenz law. if you push a magnet or pull a magnet toward a coil, the current can be produced in different directions. See, if you move it away, it would be down in front. If you move it toward, it could be up in front, right? So you just move it back and forth. The direction of the current will change, depends on the direction of this your magnet moving, right? If we have ability to push and pull magnet toward an innovative coil, we can alternate the current, the direction of the current means alternate means just make it back and forth. So when we have alternate currents, do you see we have this sign just going up, down? And if we have just direct current, it's just one direction, true? But alternate current going to be both direction. There's another visualization for that. When AC, you see that. DC is just a battery. Here is the picture. So you have the current going up. If this is going in positive direction, so the current increase, then the current decrease in positive direction. Then it changed the direction. When it becomes negative, it means it's just going backward. And then it going forward and then going backward, and it's just alternating happens. So if this is a time, it would give you the period, right? Okay, so now I'm gonna just quickly go. So what we use AC circuit in our homes. I think you need to know. As you see in a graph, the voltage and current oscillates, some maximum positive voltage and some maximum negative voltage. Since this only occurs twice each cycle, we use a root mean square as an effective voltage of what a home typically has available. So don't have to do this, but I want to tell you, if this is going up, it means the current increase. Going down means the current decrease. When it becomes negative means the switches direction and increase in that direction, then decrease in that direction. Okay. Now, just quickly go over these wires, and that's it for this slide. Most common appliances require no more than 120 volt, whereas some heavy duty appliances require up to 240. So our AC circuits equipped to do so with a wire configuration seen to the right. We have these hot wires, which are red and black. We have these neutral wires, and we have the ground for protections. So we have 4 things here. Sometimes you don't have this protection and grounding. This is 2-wire cables. This is the 3-wire cables. Look at this. So you see here 4 things going inside. Here is 3 and here is 2, right? To get the full 240 volts, all 4 wires must be used. Like this is a plug, and you see that there, right? The 4 ports. Just plug that in here. It's 240. Some country, they work with 240. You see that. Some country working with 120. They have 3. Appliances needing only 120 or less. Use only black wires, not red. The white and ground are still used, has 3 prongs and holes. So if you have a risky lamps, they just have a 2, they do not have a grounding, right? So that's it. I'm gonna